We're going to start with the not a weak acid. I wanted to bring this up because we want to compare and contrast. When we end up doing a titration, this flask has the analyte. This contains the solution we're interested in. This is the solution we measure the pH of. We're seeing what's happening to the pH in this flask. This is our burette. You really should watch the beautiful video that I've got in the previous week where they show a titration. It's the best video I've ever seen of a titration being done. So that one is worth watching. Here's our strong acid. And no, it's got to be a strong acid because look, right here, down here with a pH of 1. I mean, it's almost impossible not to get a pH of 1 with a strong acid solution. If you get anything more than like a few drops of acid that you make the solution up with, you're going to get pH of 1. So that's the giveaway. So that's right here. We got a pH of strong acid, one that then we put drop by drop by drop by drop of our base in here. And you'll notice nothing much happens. This stays pretty close because even as you wipe out the acid in here, there's still enough to keep this pH really, really low. And it'll just keep on going until finally there's virtually no acid left, but still we got a pH about 2, but a couple more drops and zap, it's all gone. And we're at the equivalence point. And look here, you're going from 7 point something to 8. And just a couple of ml, a fraction of an ml, and you get this huge change, a radical change from 4. This is it. Flat, zap to the equivalence point, which is the important part. That's where you can find out. This is where you wiped out all of this analyte, this acid. And if you know the volume of base you had and its concentration, here's your volume of base that you're going to have here, volume of titrant. Then you can do Ca, concentration of the acid that you're solving for, times the volume of the acid that you had in here. So, okay, now let's go to weak acids and bases. Well, first of all, we've got our weak acid in our flask here that we measured the amount of carefully. And when we start, when we haven't dumped anything titrant in yet, we've got a pH of greater than 2. And that's the giveaway for a weak acid, weak base system. At first, when you add this strong base to it, it starts wiping out that weak acid. And the pH starts going up. So we go HA plus hydroxide produces a little bit of our conjugate base. We have less acid. Now there isn't very much A in here, almost no A minus. But when you get to a certain point, you start getting significant amounts of A minus. And that A minus acts as a buffer and prevents a pH change. Without that buffering, this thing would just swoop up. But no, you're going to have this buffered area that's part of the way through your titration. And the critical part is, when you reach a point, you've gotten rid of half the acid. You reach what's referred to as the half equivalence point. So if you knew it took 8 mLs to neutralize all the acid, the 4 ml point, that point is the half equivalence point. Given a titration, you say, okay, I did this. I saw the color change. Or I found out that the pH, this is where we had our inflection. This steep curve indicates that you've gotten rid of the last of your acid. The steep part of the curve indicates that there's no acid left. In fact, when half of that is the half equivalence point. Yeah. Well, what's so big about a half equivalence point? I've half titrated it. What does that mean? Well, when that happens, your A minus equals your HA. The log ratio here is going to be 1, and the log of 1 is 0. That means the pH at this point looks like it's about, I guess about 4.3 here. The pH at that point, right there, is going to be equal to the pKa. Now that's good. You found out a very, very important thing about the acid. I mean, when you find the equivalence point, you know how concentrated it was. But if you know the pH at the half equivalence, you know the strength of the acid. You know it's pKa, and you can find its Ka. So the half equivalence point right here, you can imagine people writing AP exams saying, okay, let's see if this person can find out yeah, how much it takes to neutralize the acid. But are they going to be able to find out how strong this acid is, what its Ka is? And that's where you get this half titration, half equivalence. Once you get past that buffered section, then you get the steep curve and you reach the equivalence point. Notice that the equivalence point is greater than 7, and the reason it's greater than 7 is that you have just, this is wrong, you just have A minus, you just have conjugate base. So you have a mildly basic solution. Right here, you're not stuck with neutral water, but you're stuck with a mildly basic, changed all the HA into its conjugate base. And as soon as you add some extra base to it, this thing just, you've got hydroxides all over the place. At the equivalence point, the same equation works with your strong acids, strong bases. Now, it's just that your pH at the equivalence point is going to be 8, or maybe 8.5, or even 9 if it's a strong conjugate base. But at the proper equivalence point, this equation is going to work. A little contrast. Here, we've got a steep coming up, flattened buffer, steep part, and then who cares about the rest of this? That's not important. A strong acid, flat all the way through, and then a shoot up. There's not that little up, flat, and then up again. Base acid neutralization, strong and strong. You start at a very high pH, lots of hydroxide ions, and then zip down. I don't think I have to say anything here. You can see this is pretty flat, and then the line, it's a line, it's a line. In fact, that's how they mathematically analyze this stuff when they've got a machine trying to interpret a pH graph. Now, let's go for the weak base. So we've got our weak base down here. This is our solution that we're starting off with. And notice, we're not starting at 13 or 12. We're starting at like about 11. You end up dropping the pH pretty nicely as you add some strong acid to it, but then you get a buffered solution. You get a leveling off. Notice that this is going down, then you get a leveling off. Finally, your buffer is wiped out, and you reach your equivalence point. And again, the equivalent point is going to add a pH that is not 7, but less than 7, because you've turned the base into its conjugate acid. Basically, you've made acid a weak acid, and that's your equivalence point. One thing that's a little tricky, we still have a half equivalence point. We have a half equivalence point, maybe 8.5, 8.6. Now, a common error is at the half equivalence point. If you're interested in the base, the POH will give you the pKb. If you want to find the strength of the weak base, don't use this number. That's the pH. Use, in this case, 14 minus 8, 6, which is the POH. POH is 6, because these two add up to 14. I'll put a plus there. Oh, that's not a very good plus, but they add up together to make 14. So you can find the strength of the base from the pH, but you got to subtract the pH from 14. This is the same. Ca, Va, the only thing is your equivalence point's now going to be acidic rather than basic. Now, one thing I've noticed on a lot of the more recent tests, they only show you half the curve. Now, this other curve, and really, who needs the rest of this curve? That's you're way beyond what you should end up having. It does continue, yes, but who cares about that? So don't be fooled when they show you just going up to this part. Most people end their titrations. Once that pH reaches of this equivalence point, you stop. I mean, why go any further? Okay, go through your notes. The notes really, I think, do a better job explaining this. This is sort of a summary. You've done lots of questions on these, so good luck on the exam.